And I think we should get going now. So I'm gonna start by introducing today's speaker. Today's speaker is Dr. Zohreh Davoudi, and she received her Bachelor of Science in 2007 and her Master's of Science in 2009 from Sharif University of Technology in Tehran, Iran. She received her PhD in 2014 from the University of Washington in Seattle, and shortly thereafter, she joined MIT's Center for Theoretical Physics as a postdoctoral research associate. In 2017, Dr. Davoudi became an assistant professor of physics at the University of Maryland, College Park. Her research explores strongly interacting systems, such as hadrons and nuclei, using analytic and computational methods, including effective field theories, lattice quantum chromodynamics, quantum simulations, and quantum computing. She's a recipient of the Kenneth Wilson Award for Excellence in Lattice Gauge Theory, the Alfred P. Sloan Fellowship, and the US Department of Energy's Early Career Award. So with this introduction, I'm going to hand over the virtual floor to you, Zohreh. Thank you very much for coming and offering to give your talk here.
Thanks very much, David, and the rest of the group for inviting me. I appreciate it. It's a pleasure to be here. Let me make sure to hide this panel. All right, great. So let me get us started. What I'd like to try to convey today is what developments are happening in simulations of gauge field theories, in particular with quantum tools, now that we are in an era that there is a promising future for the use of quantum technologies in simulating physical theories, and in particular, what is of interest to me and a number of people in the community is how to simulate gauge field theories that are the interactions of a standard model of particle physics, what describes most of the fundamental forces and interactions in nature, and how we can go about simulating nature starting from these fundamental building blocks. So I think this crowd probably doesn't have sort of the background on the high energy physics side of things, more on the quantum computing and simulation side of things. I try to have that in mind, but if there is any technical term I'm using unintentionally, and it's not sort of conveying what I'm trying to say, please ask questions. I try to explain it in terms that hopefully would make more sense. So I apologize in advance if that's the case. All right, so let me get us started. I want to tell you that my background is in classical simulations of lattice gauge theories, a program that is called Lattice Quantum Chromodynamics, or Lattice QCD. And being involved in this program is the reason that I started to think about how we can also take advantage of quantum technologies and quantum simulation in advancing lattice QCD simulations as well, kind of going beyond this classical approach to the simulations in our field. So I need to tell you what is involved in classical simulations of these quantum field theories, first of all, so that I can motivate why we think that quantum simulation technologies can help us move forward with the hard problems in this field. So why do we simulate quantum field theories? We are interested in simulating particularly a strong force. And the theory of a strong force is called quantum chromodynamics. So that's what I call QCD. This is the theory that binds quarks and gluons to form the hadrons and nucleons and an atomic nucleus. So kind of the building block of matter in the universe is really sort of sitting on this description of the strong force in terms of quantum mechanics and relativity. And the numerical tools that we use to simulate the theory is called lattice QCD. All right, so let me tell you what QCD is all about, this theory of a strong force. And it is, for those of you that might be familiar with this technical term, It's a gauge theory, and it's non-abelian SU3 gauge theory with several flavors of massive quarks. So this is one of the few equations that I'm going to show in this talk, but I think it's interesting to remember that the equations that we write down for quantum chromodynamics, in a sense, are simple. I mean, of course, they are more complex than electromagnetism or quantum electrodynamics for the theory of a strong force. But in the end of the day, it's just like two lines of equations. There are interactions of quarks of several flavors with the gauge fields in this term, for example. So this is the kinetic energy of the quarks. This is the interactions of the quarks and gluons in nature. And this last term is the interactions of the gluons themselves. So this is a term that, for example, you don't see in quantum electrodynamics, the theory of photons. This term is really specific to the gluons and a strong force. And that's why this theory is so much more complicated in the end of the day than QED, and it has very interesting features. So what are some of those interesting features where, if you look at this theory, there are only a few input parameters. You need to know the masses of the quarks and the coupling constant between the quarks and gluons, which happen to be the same coupling constant between the gluons themselves. And once you have these parameters, maybe plus the coupling constant of QED, quantum electrodynamics as well. And then if you had a powerful enough computer, in principle, you can simulate the entire hydrogen nuclear physics by these two lines of equations, which is remarkable. Nature works with just a few input parameters, and all the complexity seems to emerge from the interactions, from this complex dynamics, these interactions of quarks and gluons themselves. And these interactions are becoming as strong because the theory is called asymptotically free. There are confinement and things like that. So it's not like we can do pen and paper calculations here. We really have to simulate the theory exactly in a computer. So that has started a very large program. And you might ask, how do we start simulating a theory? Well, one of the natures of this theory is that it's quantum mechanical, of course. So we have to impose quantum mechanics in our simulations. What does that mean? Well, let's just go back all the way to what Feynman told us about simulation. This is about quantum mechanics. If you have a system A and it progresses to system B, the probability amplitude of going from A and B classically can be just described by a single path or trajectory. But of course, quantum mechanically, there are infinite number of trajectories to take you from A and B. And what nature does is to perform a weighted average over all these paths that have each own weight. And the classical path is, of course, has the largest weight. But in the end of the day, nature does the sum over infinite number of possibilities. So if you want to do a quantum simulation of, just a simulation of QCD itself, we have to make sure to incorporate this quantum mechanical feature, which means that we have to sum over all the possibilities for the configurations of the quarks and gluons to be able to get the answer right. That's one feature, but that's not all. We know that if we combine quantum mechanics with relativity, we end up with the theory of quantum field theory. What does that mean? Just very schematically, once we have a field theory, then we are dealing with configurations of fields that can be complex in general. What that means is that, for example, if you're interested in the probability amplitude of going from A to B, even if A to B is just like vacuum to vacuum, no particle, no excitations of the fields, it's not a trivial calculation because you have to do this on the background of all the configurations for these fields now. So this is very schematic. And of course, now if you're interested, for example, in the correlations among particles or fields, to be more concise, to be more accurate, then we also have to do this correlation calculation on top of the configurations of the vacuum itself. So that's why simulating a theory like QCD is very non-trivial in the end of the day. It's not like sort of the classical non-relativistic type of simulations that we think about, for example, in spin systems or sort of any classical simulation that you can think about that doesn't sort of incorporate this field theory nature to it. And I come back to this in a moment. So let's have a look at how these conventional lattice QCD simulations of nature are being performed. What is sort of the workflow? So this is the workflow. As I said, we have to generate a large sample of configurations of the vacuum. Vacuum in this context means all the gauge field configurations, all the gluonic configurations that we have to then evaluate the correlation functions on top of. So in that schematic picture, there are many different configurations with their own weight that we have to include in the computation. So the first step is to actually generate these with their own weight. And of course, this is going to be sort of a statistical process. We have a finite sample of these configurations. And hopefully, if we have done our job correctly and we have enough of these configurations, then we can take the limit of infinite configurations and recover the number that would be in nature. So this is an important sampling problem. We do it with hybrid Monte Carlo. And at the end of the day, it's a very costly calculations because we have to do a determinant of very high dimensional matrix. By very high dimensional, I mean the dimension is like millions. So this is very costly, as I said. And one of the things that would allow us to do this is actually to go to Euclidean spacetime, because if you're working with the real time and Minkowski time, then we cannot do this Monte Carlo sampling as it turned out, because we don't have a real weight for this sampling. So this is one of the limitations of this conventional approach to lattice QCD. And you see that this is a big limitation, and that's why we want to go beyond this and do quantum simulation, because this is really kind of limiting us, but nonetheless has provided a very powerful tool to compute observables in QCD. So this step is, as I said, it creates the vacuum configurations for us. This is a real lattice QCD simulation, this video that you can see of simulating the gauge field configurations. So that's a step. The next step is to compute correlation functions, as I said. So now we want to see if we have multiple fields, how they correlate, because out of correlation functions, then we can compute observables. So again, this step can be costly as well, because we have to find all the possible combinations of the fields at the source and sink for our observables. And it would be a very costly part to actually figure out all these combinations. But then also we have to invert a high dimensional matrix again. So that matrix of millions of dimension, we have to, again, deal with it in this step as well. But then eventually this gives us things that are interesting. You can see, for example, confinement arises from this picture. For example, if you have a quark and anti-quark, like in this picture, they can create sort of flux tubes. And you can see really this phenomenon of confinement arising non-perturbatively out of these calculations. And then finally, there's a step involved in analyzing correlation functions. We have to do a lot of numerics and analytic work to relate these numbers to the numbers in nature. So I won't go through this, but eventually we get something like an atomic nucleus, which is amazing. And in fact, let me tell you what is accomplished so far very briefly in that regard. One of the milestones in this simulation program, starting from QCD, happened a few years ago by a collaboration that I'm part of. At the time, I was not in the collaboration, so I should not take credit for this nice work. But in any case, in 2013, this NPL QCD collaboration was able to show that if you start from the quark and gluons and perform this procedure, this very costly, lengthy procedure that I described, you can end up getting an atomic nucleus out of the quark and gluon degrees of freedom. So this plot shows the binding energies of something like the deuteron or helium-3 or helium-4 or even objects that are more exotic, like this strange nuclei that people are searching for in experiment. One caveat in this picture is that this is not quite a picture in a physical world, because in order to make the calculations less costly, we work at a quark mass or pion mass that is heavier than what it is in nature, because then this would allow us to do that step that I talked about, inverting large matrices, to be easier for technical reasons that if you're interested, I can tell you about later, and for other reasons. So even with these very high pion masses, that eventually shows that you can get atomic nucleus, and we're working at lighter pion masses at the moment to recover the same picture. Even with this very large mass, you might ask how many, how much of a computation you're talking about when you say these computations are costly. Let me give you one figure of merit. So for example, this study that I showed in the previous picture, it took 2 years of running and a few 100 million CPU hours on the largest supercomputer at the time. I don't think it was Titan at the time, but I'm just showing a picture of one of these large supercomputers. So we're talking about years of effort to get a picture that is nice, and it shows that, yes, complexities in nature arises from simple interactions of quantum chromodynamics. But even this picture, which is like still at high values of quark masses, took years. So now you can imagine it would be much more costly to go beyond this picture and to go to a larger nuclei and also physical. We've done even more interesting calculations. We have looked at, for example, reactions of these light nuclei. We have looked at the rate of reactions of proton-proton fusion starting from quarks and gluons. This is something that was a dream 10 years ago or so, but this has now been accomplished. So we're very, very happy about this. And a lot more examples that I can give you to say that really this conventional lattice QFT approach, while being costly, while being complicated and non-trivial, have given us very surprising and interesting results that we could not have previously. So this field is really progressing. But the question is that, can we go beyond the current studies? What are the limitations? Well, some of the more prominent limitations that I can talk about are probably two categories of questions. One is studies of nuclear isotopes, dense matter, phase diagram of QCD. For example, this picture that I'm showing, we would really love to know this quarks and gluons. If we crank up the temperature or chemical potential, can we recover or write or plot a phase diagram as accurate as it is for something like water, right? I mean, what is the phases of this strongly interacting matter? And we have some idea, some conjectures here and there. We know there might be quark and gluon plasma. There could, of course, we know there are nuclei. We know that there are neutron stars. Maybe there are more exotic phases. Maybe there is a critical point. And there are experiments that are trying to explore this, but unfortunately, theory has been very limited because these simulations that I talked about, they run into a sign problem as soon as you introduce a finite density or finite chemical potential. And this is kind of technical, but it comes back to the fact that we do Monte Carlo sampling and we need real weights. So as soon as we introduce a complex number into our action, just like the usual fermion sign problem that you might have heard of in the context of condensed matter, this is similar. So we have been very much limited to just like going along this axis, but not being able to go along this axis. So this is one of the things that we would like to change. Another topic is real-time dynamics of matter in heavy ion collisions or after Big Bang. So again, remember I told you that we have to make these calculations to be performed in Euclidean spacetime or in imaginary time. But on the other hand, for processes that are real time, we really need to work in real time. So we have now an imaginary weight for this Monte Carlo simulations that is not going to give us anything useful. There's going to be a severe sign problem. if we want to do Hamiltonian evolution as opposed to this sort of path integral evolution, then it's the same thing, because the dimensionality of the Hilbert space is exponentially large in the degrees of freedom that we introduce, and well, it is not possible. And we all know that the Hamiltonian simulation is much more costly than what we can afford at the moment with classical simulations. So we're very much limited, and we cannot look at a whole bunch of interesting physics, including non-equilibrium properties of a strongly interacting matter, just simply because our calculations are designed to work in imaginary time. We would like to go beyond this. And this is really takes me to the next part of my talk, which is whether or not we can leverage quantum technologies to go beyond these limitations and do better. And in particular, be able to do real-time dynamics, for example, for these theories. I'm going to pause here and see if there are questions for this first part before I move to the different topics.
I see that there's one question from Stefan in the Q&A button. He's writing to ask, can you say what one such configuration would be? Is it the function of space-time? Is it a classical object, not an operator valued, for example? I guess this was quite a few slides back.
Yes, so I can briefly tell what I mean by these configurations. So in end of the day, remember I told you that QCD was an SU2 lattice gauge, SU2 gauge theory, non-abelian theory. So SU3. And so these gauge configurations in the end of the day are SU3 matrices. Okay. So now I have a SU2 matrix at each single space and time point. So one configuration amounts on what the value of this SU3 matrix is for all the points on the space and time. And of course I discretize, so it's a lattice, but still I have to know all the values of these matrices. Now, then I have to let the system evolve with the action of the theory. So at the next step of my Monte Carlo, then I have a different configuration, which means that the values of these matrices gets updated as a result of that. And I do this process many, many times to be able to make sure I have recovered all the possible configurations given the weight that I give in the action. I have to make sure to get rid of all correlations as well, right? So this, I have to end up with decorrelated configurations and so on and so forth. So then in the end of the day, you have a good statistically uncorrelated sample of configurations that you can measure observables on. Does that make sense?
Yeah, I think that probably should answer it.
All right, good.
Stefan, if you wonder anything further, just maybe update the question in the Q&A button.
Great.
But I think that was clear. Thanks.
Good question. Yeah, that shows that I should have probably included more detail. It seems like there's some interest. But anyway, make sure to ask me afterwards if some things are still not clear. All right, so let us talk about quantum simulation. Now let's see what it amounts for this program of nuclear physics, or what is called high energy physics, I guess, in Europe, I realize. So some of the topics I'm calling about has a different name in Europe, but according to the divisions in the US, they're more in the realm of nuclear physics than high energy physics, but at the end of the day, it's just terminology. It's just trying to solve for properties of matter starting from a standard model. That's the program. Anyway, so what we would like to do in quantum simulation is, of course, to leverage another quantum system that can be controlled to study another quantum system that is more elusive experimentally or computationally. So, of course, I gave you an example of a quantum system that we would like to study, but it's very elusive, both experimentally and computationally. That's QCD. And that's sort of in this picture, the quarks and gluons making this complicated nucleus, and the nucleon, and the nucleon is making a complicated nucleus. And then we know that then these form atoms and molecules and material and then more macroscopic objects. But the interesting thing is that now we would like to use these atoms and molecules and materials that are fundamentally like different in terms of scales and intrinsic interactions and so on from the objects that is on this side, the nucleus and nucleon and quarks and gluons, and simulate this desired system using a set of other systems that are available to us, whether in a digital way or in a more analog way. So that's really the quantum simulation program for this field. And of course, this is a good time to start thinking about this, because as we all know, there are varying, there are quantum simulator technologies with varying capacity and capability at companies and the US national labs and in everywhere in the world, from Europe to Asia to the US. I've been biased in this picture towards North America, but of course there are a lot of efforts now in everywhere in the world to really make sure that soon enough we will have reliable, scalable, noise resilient quantum computing and quantum simulation technologies with various different architecture. So we're not there yet, but it's a good time to start thinking about that future. If someday we will have good enough and powerful enough quantum computers, are we ready to do a lattice QCD simulations with them? That's the question. That's the effort. So again, the question is, can we adopt quantum tools and algorithms from other communities, for example? Because this has kind of started quite early in communities like quantum chemistry and condensed matter. Have they developed enough tools for us to take them and then push this program of lattice gauge theory simulations, QCD simulations? Well, it turned out that yes, a lot of technologies we can just sort of port to the other side and use them. But unfortunately, there are also major differences here that we have to keep in mind. And kind of goes back to this property of that I was talking about. QCD is really quantum field theory. So even if you want to start from just nucleons and forget about QCD and quarks and gluons and say, someone would tell you what the Hamiltonian is for interactions of 2 nucleons and 3 nucleons and so on. Can you simulate using quantum computers the dynamics of the system? Well, yes, but it's more complex because the Hamiltonian itself is more complex. It has short, intermediate, long-range interactions. It has even 3 and multi-body interactions, something that you don't often see in other problems. There are bosons, these are pions and other hadrons that can become dynamicals. So in the end of the day, it's a much harder problem now, for example, a quantum chemistry problem. But it's closer compared to if we wanted to start from a standard model. So sort of this program of lattice QCD that I was describing, if you want to do the same thing with quantum technologies, then it's a lot more different than what other communities might have been used to, because again, it's a quantum field theory. Why? Well, now we have both bosonic and fermionic degrees of freedom that are dynamical and coupled. The theory exhibits not only global, but also local gauge symmetries. The theory is relativistic, so particle number might not necessarily be conserved. And the vacuum of the theory could still be non-trivial if you're dealing with a strongly interacting field theory. So a lot of the features in non-relativistic sort of quantum chemistry type problems are kind of out of the picture. And we have to start thinking about maybe coming up with the specific algorithms that make these calculations possible. So that's really the program. So what does quantum simulation of gauge field theories involve? All right, so that's the question. If you want to go through this path of starting from a standard model, what is it that you have to keep in mind? What are the non-trivial features? So let me very briefly tell you what they are. I would argue that this whole program would involve multiple efforts in different sort of categories. We have to do theory developments. I tell you why. And there has to be algorithmic developments, of course, but also implementation and benchmark on real-time, on near-term hardware. That's also very important because that would let us understand what the limitations are, and would probably help us to sort of come up with co-design strategies to maybe have a sort of single purpose kind of quantum simulators of lattice gauge theories, if that's the way forward. So that's something that would be worth investigating. So let me tell you a little bit about the theory developments. Well, quantum simulation of gauge field theories would be better to go through this Hamiltonian formalism, because conventionally we work with path integral formalism in classical simulations, as I told you about, because we want to do Monte Carlo sampling and all of that, right? But now we don't have to, because the quantum computer or quantum simulator is more natural to work with Hamiltonian. It can intrinsically easily perform unitary time evolution. So that's why Hamiltonian formalism is more natural. So again, this is one of the few equations that I'm writing on this slide. What would be the Hamiltonian of the QCD like now? Because in previous I showed you the Lagrangian, and now I'm showing you the Hamiltonian. So you can derive that this Hamiltonian from that Lagrangian in sort of a lattice gauge theory when things are discretized. And again, there are only 4 different terms. Okay, so it looks simple looking, but in the end of the day, it's quite complicated actually. Not only you have the fermionic hopping that goes through interactions with the gauge links or gauge fields in this case, but also you have the mass term, in this case a staggered mass term, electric field term. This is a non-abelian theory, so you have left and right electric fields. But this complicated what is called a magnetic field term or plaquette term, which involves, for example, 4 body interactions. 4 of these U's are sitting in each of these terms. So it's a complicated Hamiltonian in the end of the day. There are 2 important features about this. One is that we are dealing with gauge fields, and these are bosons. And the bosons have an infinite dimensional Hilbert space. It's not like just fermions that we map them to qubits. Now we have to map these bosons with infinite dimensional Hilbert space to qubits. That's not possible. We have to truncate the Hilbert space of each of these fields at each space point to be able to really fit this into any finite quantum simulator or computer, right? So that's one feature. And then you start to ask, well, what are the truncation effects? And then we have to start to really study this carefully and make sure that our observables are converging to the right value if you put certain cutoff on the excitation of these gauge fields. And this is the study that, for example, we've performed with given formulation of the theory. Other people have started to look into this with other formulations, but that's one of those theory developments that I was talking about. And what we see is that for low energy properties of the system or for short time evolutions, observables converge to the right value exponentially fast. But as soon as you are in the sort of high energy regime or high time evolutions, then you start to see a lot of irregularities, and you need very large cutoffs to be able to describe the theory properly. So that's one of those theory investigation that has to be performed. All right. Another feature, the second feature that I want to highlight before I just move on from this theory developments. There's a very important constraint that we have to keep in mind. The theory is gauge, has a gauge symmetry, has a local symmetry. And in the Hamiltonian picture, what it means is that there is a Gauss's law at each space-time point. And you're familiar with Gauss's law from electromagnetism, right? It's just the statement that the flux of electric field has to balance with the charge, with the electric charge at the given point. So now you can generalize this to the abelian, non-abelian theories like QCD. Again, sort of the flux of this non-abelian electric field has to balance with the SU3 sort of fermionic charge. And this is a complicated relation in non-abelian theories because there are multiple relations here and they cannot be diagonalized at the same time. These are non-commuting operators. But in the end of the day, the physical sector of the theory is the one that is annihilated by this Gauss Law operator. So not all the Hilbert space of the theory is physical. And like schematically, what it means is that if you naively form the Hilbert space of the theory, only a very small part of it is physical. And you better start your simulation in this part, and you better do it in a very gauge invariant way, and you better have a perfect hardware so that you don't spill out of this small Hilbert space and end up in this vast unphysical Hilbert space, which is sort of very inefficient in terms of the simulation. So again, we've let me not go through this as much, but just like showing in a particular example that the size of the Hilbert space is still exponentially large, this physical sector, but on the other hand, is orders of magnitude smaller compared to the size of the full Hilbert space. So again, it's important to come up with the strategies that would allow you to use best use of your resources to stay in this small sector. You don't need to simulate the entire space, and you have to make sure that the errors in the simulation won't take you out of this sector. There are some ideas out there of how to deal with this, and one of them is kind of interesting. You can start to introduce random unitary sort of operations, just like single qubit rotations in between your trotter steps, because even like trotterization of the time evolution operator can break the symmetries in your theory. Of course, we know that it's not always possible to come up with a product formula for time evolution operator in such a way that it preserves all the symmetries of the original theory. And in this case, in this nice paper, they show that for this lattice gauge theory, coming up with this sort of protocol of inserting these random rotations, you can actually suppress quite a bit the leakage to the unphysical sector that I was talking about. So people are starting to think about how to deal with this issue. And there are some other similar ideas that came out of Europe. This is very interesting. They take advantage of using the Gauss Law operator itself to introduce these rotations and then suppress this leakage to the unphysical sector. So this is the kind of theory developments that I was talking about. You have to understand your theory, you have to understand the constraints and symmetries, and you have to make sure to come up with simulation protocols that would preserve them. Otherwise, you're not going to get the physics that you would like to get out of these simulations. All right. So the next part is algorithmic and implementation. I want to talk about both at the same time through one example. And this would be really sort of the last part of my presentation. But I think it's a good point to pause and see if there are questions about what I just presented.
So I can't see any questions at the moment. If anyone has an immediate question that can't wait until the end, maybe just raise your hands now. Or otherwise we will keep going. Yeah, I think we'll just keep going, and then we'll take questions at the end.
All right, sounds good. Okay, so algorithmic developments and also implementation and benchmark. Well, I don't have to tell to this audience what are the different approaches to quantum simulation, my guess is, but let's just briefly say what I mean by these approaches. So one of them is, of course, an analog approach. When you have a quantum system that is hopefully sort of flexible enough in terms of interactions and in terms of the control, that you can engineer exactly the Hamiltonian or semi-exactly with some approximation, the Hamiltonian of the system that you're interested in. And therefore, if you start your experiment in this simulator and the system would evolve with the exact Hamiltonian that you have in mind, and then you end up with the answer, right? So that would be one approach. Unfortunately, we don't have a lot of these simulators that have enough capabilities and control to enable simulating theories that we're interested in. In particular, something like QCD is very complex. So at the moment, we don't have the hardware with intrinsic interactions that mimic interactions in QCD or even simpler gauge theories. So we have to think about other strategies. Of course, digital or universal quantum computing is probably the best strategy if we have this system someday in future, right? Because then we have the freedom of or flexibility of engineering all sorts of interactions, because then you just break down the time evolution operator to smaller steps if you are dealing with certain types of Hamiltonians. And each of these steps then can be decomposed into a universal set of gates, either single or 2-qubit entangling gates, for example. Of course, there's going to be a digitization error, and the circuit could be really complex in the end of the day and high depth and might not be very efficient, at least for near-term hardware that is limited by noisy implementations of these gates, right? There's also an approach sitting in between that I call it analog digital or hybrid approach, and a lot of people talk about this. I want to give you examples of this in the context of a gauge theory example. This is when you use, you still digitize the time evolution operator, so really it's a digital protocol, but you go beyond the standard set of gates that is available in the digital universal computing. You also use the fact that you can have more advanced set of gates, given that you have more degrees of freedom than just qubits in the system. So you use those degrees of freedom to encode information, but also use the appropriate gates to expand the toolkit of the quantum simulator or quantum computer. So I'll give you an example of this to see what I mean in this context. So this example requires me to pick a platform and also a theory, a gauge theory. So the platform that I'm most familiar with and worked with is trapped ion quantum simulators, which are the systems that we have the opportunity to be in a place to have these systems available to us, which is great. And the model is actually a Schrödinger model, which is the one-dimensional quantum electrodynamics. So by no means we are there to do QCD yet, but there's been progress in this, which is great. But at the moment, I want to focus on something that is a little simpler, which is still complicated, it turned out, to demonstrate the features of each of these approaches. All right. So as I said, with the digital approach, we have the single qubit gates and 2-qubit gates. They're called Mormer-Sorensen in this context of ion trap. Everyone is familiar with these gates, so this is sort of my notation. Now, in this analog digital approach, not only I have the single qubit gates and 2-qubit gates, I want to expand the toolkit to have also the spin phonon type gates, when the qubits are coupled to the phonon degrees of freedom in the system. These phonons can be normal modes of motion, excitations of normal modes of motion, or local modes of motion. We could also have something that is called a standing wave gate. And what this standing wave gate does is to couple the phonons themselves. So that's what I meant by extending the toolkit of digital quantum computing by taking advantage of more degrees of freedom in the simulator, in this case, the phonons. And of course, an analog approach is to just like do everything in one go if we can. So there is no gates. The theory I want to work with is called Schrödinger model, or one-dimensional quantum electrodynamics, which is great. It's been a test bed for a lot of ideas in both classical and quantum simulation of lattice gauge theories, because it's abelian, it's one-dimensional, but it has a lot of features of QCD, it turned out. What is the theory? Well, in terms of the spins, because fermions are now mapped to spins easily in one dimension, there is a mass term, there is this hopping term with this field, the gauge field that is represented in this way, and then there's the electric field term, L squared. It's abelian, so there's only one electric field. So there is a fermion gauge interaction, this term, and there is a sort of the electric field or gauge interactions in a sense in the theory. And then you can use the Gauss's law to eliminate the gauge fields in this one-dimensional theory. You cannot always do that if you're in higher dimensions, but if you're in this one dimension with certain boundary condition, you can actually write this as a Heisenberg model, a spin model, which is like sigma XX, sigma YY, but also sigma ZZ type interactions. And it's not just nearest neighbor, it's actually all to all sigma Z, sigma Z. So it's a more complicated spin theory than when people deal with. But anyway, so I'm going to look at both formulations, both the first part and this part when things are just in terms of the spins. Okay. So here is the trapped ion mapped to the lattice Schwinger model, this one-dimensional QED. You have fermions sitting on the side, so you have the electric field and the corresponding conjugate variable, the gauge links, sitting on the links between the fermions. And then I just mapped the fermions to the trapped ions. So these are the ions. Each of them represent a spin or a qubit because of their internal degrees of freedom can be controlled. But then the system of the ions also can be addressed because there are collective normal modes of motion, and these are used to perform entangling gates between all the ions. And this is all-to-all interactions, right? So in a spin formulation, that second formulation of gauge theory that I told you about, then everything is just a spin. So you just sort of map these fermions to the spins, but then you have to then do all-to-all interactions. So this is sort of the picture of, or a schematic of what the circuit would look like for the trotterized time evolution in this theory. You have the fermion gauge interactions, you have this nearest neighbor entangling gates, you have the gauge field interactions that could involve non-nearest neighbor and all-to-all sigma Z type interactions, and then there's the fermion master, okay? So in this spin formulation, the fully spin formulation, things are not too bad in terms of a digital implementation. And in fact, this is really the circuit that was implemented for the first time in 2016 by the Innsbruck group to show the very simple, a small instance of a real-time evolution of the Schwinger model. This really created a lot of excitement in the field because it was the first time that the actual hardware showed the real-time evolution of a lattice gauge theory and creation of pairs and all sorts of interesting things that you can imagine in relativistic quantum field theory. You can see it on a quantum hardware. Of course, it was very much limited at the time, but it was quite exciting. So that's why people really started to think about these problems. And then here at Maryland, we've really extended these simulations to much longer time evolutions because the systems are more advanced and more noise resilient now, so we can go many cycles. This is sort of a preliminary results from an experiment here in Maryland that we've been doing with collaborators here. So what else we can do? Well, you can do this in a fully analog way. So still you remove the gauge links, so everything is a spin. But then you want to do a Heisenberg spin simulation in a fully analog way on a trapped ion system. Remember, these trapped ion systems, if you know about them, they can simulate Ising model quite easily, but not necessarily Heisenberg model. So in this paper, we came up with a protocol for being able to actually do also Heisenberg model and therefore Schwinger model. It involves 3 sets of razors and very interesting optimization problem that goes on to make sure that you get the right interactions. But in the end of the day, it was doable. And in fact, my collaborators are building the experiments to actually do these simulations of the Schwinger model with this protocol. So this is an example of the optimization that you have to do to get the perfect nearest neighbor interactions, for example, in Schwinger model, for the laser parameters and amplitudes and frequencies and so on. And this is an example of the long-range Coulomb interactions that you can perfectly optimize and get out by the right laser parameters. So we're very excited about this, and I think this would be demonstrated in the next couple of years. But what are the other approaches? Let's say that you don't remove the gauge degrees of freedom because you can't always do that. So let's not like cheat and let's just keep them, because this is a reality of life. If we go to the higher dimensions, we have to be able to deal with them. So one of the approaches in a very digital way is to say, all right, what are the excitations? How many excitations of these electric field basis I want to take in my simulations. There has to be a cutoff on these bosonic excitations. Let's say that cutoff is lambda, and these are just integers in the end of the day. So we can just assign logarithm of lambda number of qubits to represent each of these gauge lengths. So you already see that we need far more qubits to represent the gauge links as well. So let's say they are sitting between the fermionic qubits. Then what the quantum circuit would look like, let me skip this. This is another nice demonstration of this on the IBM machine with this by the Seattle Oak Ridge group. Let me tell you about the circuit and resource analysis of this approach now. So this is a circuit that was written down in this nice paper and quantum algorithms for the Schwinger model. And as you can see now, you have far more complexities in your circuit. And in particular, you have multiple entangling operations between the gauge and fermion registers, but also between the gauge registers themselves, because electric field theorem would connect and entangle many qubits that are representing this gauge degrees of freedom. So if you do a counting of the number of entangling gauge or C0 operations, you end up with orders of millions of C0 operations to get a good accuracy on the observables, according to this paper. So it means that quantum simulation of even simplest gauge theories is going to be really costly. So that's one thing to keep in mind. These are quantum field theories, so they have very different resource requirements compared to some of the models that you might have heard of. But we shouldn't get discouraged. This is the most naive algorithm that one can come up with. Maybe there are techniques and ways to actually simplify this. And this is an active area of research. And I think this would help to actually maybe come up with better resource requirements in the upcoming years. So what about this analog digital that I'm very excited about? And this is one of the recent work that we did with my collaborators in the trapped ion systems. Experts on the trapped ion systems. Well, here now we don't map the gauge degrees of freedom to the qubits. We map them to these local phonon excitations of motion. So we use the phonons as bosonic degrees of freedom to map these gauge links. So we're using them. All we got in this quantum simulator at our advantage, instead of really doing the sort of digitized approach to the problem using the qubits only. So this is interesting because then the circuit really gets simplified. We can couple the phonons or these gauge fields to the fermions, just like with a simple operation that is right here. And then the electric field interactions, that huge circuit that I showed you is going to end up with very simple standing wave gates that you can do to couple the phonons, which is nice. And in fact, if you perform the resource requirements between the analog digital and digital simulations, you see huge difference. It's polynomial, it's not exponential, but in near term, this matters, right? So the number of the n is the number of sites in the theory, and lambda is the number of excitations on the electric field. You get huge, at least theoretically on the paper, it seems like you get huge advantage out of this. And this is something that really excites us. Let me skip this, because now in this trapped ion systems, it is possible to control and manipulate the phonons as well. This is an experiment that was done by Norbert Linke and collaborators a few years ago here in Maryland, when they show that they can demonstrate the phonon hopping in experiment. This is 3 ions, and these are basically excitations of the phonons as a function of time that they can actually measure and map. And it's sort of like I think very exciting, right? It tells us that maybe it is time to also think about these phonon degrees of freedom besides the qubit degrees of freedom in the trapped ion systems. And in particular, if that's a reality, then we can start to think about more efficient and larger instances of simulation of gauge field theories as well, and maybe other fermion phonon models. And with that, as a final word, I think we are really at the end of the beginning of the quantum simulation program for lattice gauge theory. A lot has happened. But we are really at the start because there's so many things to figure out. And the next serious phases are starting right now, and we need lots of creativity, investment, theory, algorithm, experiment collaborations, and a lot of patience to be able to finally map this controlled quantum system, whether in terms of a digital quantum computer or a quantum simulator, to this strong interaction physics QCD, this very complex theory of nature that happens to describe pretty much the visible sector of the universe. So we're very excited about that. And really the last but not least, thanks to all my collaborators in this quantum simulation program. And in particular, as you can see, it's a very multidisciplinary collaboration. We have students, postdocs, and faculty members in nuclear physics, QIS and computer science, AMO, as well as other disciplines, including condensed matter. And with that, thank you very much.
Thanks so much, Zohreh, for this really, really interesting talk. It's very different from things I've been looking at in quantum computing before. So this was super interesting to see. I see we already have a question from Stefan, but let me just repeat for everyone else. If you'd like to ask a question, now is the time to either press raise your hand or ask something in the Q&A button. But let's start with Stefan, if you can join us here. Let's see. Stefan, I think.
Yes, can you hear me?
Yeah, we can hear you.
Well, hello, everyone. Thank you very much for this very, very stimulating talk. I have 1,000 questions, but I'll try to ask one. Actually, I had a bunch of questions before you started, and you answered quite a few of them, so I really enjoyed your talk. You put the bar very high. You start with quantum chromodynamics and gauge field, relativistic gauge field theories, and you want to simulate them, which is, of course, a very difficult task. And then at some point, you said something I maybe don't agree with. You said, well, if you were just interested in simulating systems from quantum chemistry, that would be much, much simpler. But I'm not so sure. And let me give sort of an intermediate example. Suppose you want to understand the motion of an electron in an ionic lattice, okay, which is, and so you want to see how it couples to the vibrational degrees of freedom, phonons. You talked about them actually, and so this is linked to, if you put an extra electric field and maybe a magnetic field, you can talk about Anderson localization. You can talk about the quantum Hall effect. This is very difficult to simulate. This cannot be done on a classical computer. And there is very little theory that really deals with it. There's a lot of open questions that nobody knows how to answer. And and I'm not sure what the degree of difficulty is between simulating a very large electronic system, simulating what I just gave as an example, and then simulating quantum electrodynamics, because in the end, you will reduce it to some finite dimensional system. And you gave very nice examples at the end. You will end up with some system a little bit like the ones you showed, the Schwinger model. And so these things will all be very similar by the time.
So can I make a comment?
Yes.
Yes, I probably wasn't fair enough in saying that statement. What I was referring to was the quantum chemistry problems that people have so far looked at in the context of quantum algorithms, which is usually just Fermi-Hubbard model, kind of to reduce it. But I totally agree that, especially if you're dealing with material science and sort of actual condensed matter systems, these are really complicated, and we all know that. I don't think in terms of the complexity, they have anything less than what I just presented. I guess what I was trying to say in that slide is that there's been a lot going on in trying to simulate this sort of spin systems or Fermi-Hubbard model in terms of quantum algorithms. Can we just like use them and simulate field theories? And I just wanted to argue that no, there are some more ingredients here that we need. So it's not like we just like take those algorithms and work with them. But that by all means didn't, I didn't mean to say that in general quantum chemistry or material science and condensed matter is much easier in terms of like complexity of these simulations. Definitely, I think these are of the same order of magnitude.
Okay, well, so great, we agree. So I have one more little question, much more shorter, I think. You showed on one of the last slides something about, well, basically a quantum simulator which would include somehow photonic degrees of freedom. There was, you had not only qubits, but also phonons somehow. I don't know if you could show your slides again.
I'm trying to do that. All right. So is that the slide that you're referring to?
No, it was before. Probably. You had these different kind of gates. It was before that, I think.
This one?
No, before.
Or the gates? Do you want the gates?
Yeah, the different. There we are. Yes.
All
so
right.
You have, yes, spin normal gates, spin local phonon gates. So are you saying people are imagining that you can build basically a quantum device in which you can control these kinds of gates?
Oh, they are already there. You don't have to build them. In fact, my collaborator Norbert Linke has a digital quantum computer that its building blocks are really sort of this normal gates, right? This phonon spin gates. You already use these interactions to induce the two spin gates. What we are trying to say here is that don't combine these two kind of, right, in a very intricate way to just have this entangling Molmer-Sorensen gate. We can also take advantage of a single sort of a spin phonon coupling that is really intrinsic to the system. That's really, as I said, the building blocks of the Molmer-Sorensen gates that they do in these experiments. So for them, they don't have to do anything. They already have everything that they need to work with these gates. The one that requires a little bit introduction of a device in the experiment is this standing wave, which means that they need another set of laser to do this standing wave gates, but that's not a problem. They can just introduce that laser. It's already there, and that's why I showed that. Let me go to this experiment. That's why I showed this experiment. That's exactly because, let's go, guys, this is so slow.
The spin phonon gate, does it act on an infinite dimensional Hilbert space?
It does in principle, right? So this experiment that I showed, it shows exactly that they have those building blocks. They've already demonstrated a simulation, a simple sort of boson hopping simulation with 3 ions, and I think this was the 3 phonon modes because they just address one set of normal modes of motions. So the Hilbert space of these bosons is infinity, right? In principle, we have to be careful. If you excite more than a few phonons in an experiment, then you run into the problem of decoherence, and then you heat up the system basically. So in the end of the day, there is a cutoff on the excitation, but it could be much higher than just doing the qubit mapping of the bosons. So you can still gain, because as far as I know, they are happy with going up to like 10 phonons or something in experiment, no problem.
Okay, well, thank you very much.
No problem. So we're excited. We hope that they can do more complex experiments with phonons for us. So we'll see.
I had maybe 2 short questions as well. So the first one, when it comes to like, it's not like super related to your exact expertise, but since you're a QCD expert, I thought I'd ask you, because I've been thinking. So this new experiment about the mu and G factor that we've heard a lot about. First, I just wanted to know, like, what do you think about it? And second, like, how hard would it be to use a quantum computer to do this like proper lattice QCD calculation of what the mu and G factor should be?
Good. So I'm very excited about this G-2 results that was announced a few weeks ago. And my excitement is basically because the experiment came out to be very similar as the one that was done over the past decades. I don't know exact date of the experiment, more than 10 years, in a different lab in the US, and kind of with independent set of people, independent set of measurements. So it wasn't really obvious that, because we've been so excited about this discrepancy between the previous experiment and theory, and that's why they wanted to do the experiment again. And it wasn't obvious that you might get the same experimental result. It would have been, if it would have been like 1 or 2 sigma to the other side, there would have not been any tension and it's over. But they reproduced what the other experiments did. And in fact, in the next year or two, they're going to have, I think, 3 or 4 times reduction in the uncertainty. So that would be a big deal, right? So this is just a start, right? So in the next 2 years, I think we know one way or another if there is new physics. That's one thing for sure. And the theory really helped here, because a few years ago, people were so skeptical about this whole vibe about sort of G-2 giving us new physics, because nobody could believe that you can get the theory right. It was so complicated. And lattice QCD came a long way, and it has good numbers with reliable uncertainties for various different bits of contributions to G-2. Even one contribution that was very complicated, light by light contribution, hadronic light by light contribution. This one was like very, people were modeling this, and they would say maybe there's 100% uncertainty. No way lattice QCD would ever get this. We have to live with the fact that this uncertainty would be there. But now lattice QCD has completed that part as well. And in fact, not only one group, but 2 independent groups, one in the US, one in Europe, have results that are consistent. So it's exciting. I think in the past 10 years, not only experiments advanced, and now we have this new results, but also theory did. So I'm actually excited to see what happens in the next 2 years. There's a theory initiative. A lot of people are putting a lot of effort and careful attention on how to interpret this theory results and make sure that different collaborations have done their job correctly and identified all the uncertainties. There are a lot of set of eyes on this program now. So I think I'm excited. Whether or not quantum computing can change I don't think at least, I mean, yes, maybe in 20 years, 30 years, but this is not good enough. Like, we need this number now. We need it in the next couple of years. And I think conventional lattice QCD calculation can do a good job. There's no sign problem. We don't need real-time dynamics. It's not the kind of problems that we are hoping the quantum computer would come and solve. It's the kind of problem that we just need bigger classical computers in the next couple of years to really reduce these theory uncertainties. So I think I'm hopeful that lattice QCD people would do their job. And in the next 2 or 3 years, we know the answer one way or another.
Then maybe just like more of a crazy question towards the end now. So we've heard here about like your really interesting research about how to use analog or digital quantum computers to solve these problems that take place in these like kind of quantum field theory fields and things like this. So assume that like in like 200 or 300 years, we have technology that can have extreme control of quantum systems at the field level. Has anyone thought about building a quantum field theory computer that does computations on these fields? Because you seem to say like, so they're intrinsically more complex, the Hamiltonians, right? So do they also have intrinsically more computational power, or do they lie in the same kind of complexity group?
That's a very, very good thought. I would say it's very interesting. I think the answer is that probably I don't know how it might work out. The only comment I can make is that I've seen one paper at least from kind of a related angle. It's by John Preskill and collaborators when they look at lambda phi 4 theory, the scalar field theory, from the perspective of whether you can simulate, whether you can build a universal quantum computer out of a scalar field theory. It's kind of related to what you're talking about, right? And it means that whether it has the ability to represent a unitary time evolution in a set of kind of universal sense out of the interactions of the lambda phi 4 theory. So I think there is at least one paper with that angle that has started. There is no kind of thinking about the hardware implementation of it or anything like that, but just like from a theoretical perspective, from the computational complexity perspective, does this theory have enough sort of computational resources, quantum computational resources, to be able to represent any computation? So that's, I think, that's an angle worth investigating. There's nothing like that for gauge theories yet.
Okay. Cool, thanks. Stefan, did you have another question there, or?
Yeah, if nobody else has questions, I have a very philosophical question. Here it is. So suppose I'm a classical physicist and I have a classical problem, and I write down a theory, and in the end, the theory is described with a complicated nonlinear partial differential equation that I cannot solve. And so I scratch my head for a while, and maybe I can't make an approximate theory either because it's out of the perturbative regime and nothing works. But then somebody says, well, but I have a computer, and a classical computer, and this thing can solve your equation very quickly. So I'm very happy. I stick an initial condition in there and I get a solution. And then I go to see an experimentalist and I said, well, I have a model for this particular physical system. Can you do the experiment? The man does the experiment. And the data of the experiment are in agreement with my computation on this computer. What did I learn? I learned that my theory mimics the physics very well, but did I understand something? I'm not sure. And so you know, when did I understand something? When did I get, if I cannot get some information out of my equation with pen and paper and a brain, what did I learn?
No, I don't agree with that. I completely disagree with that.
No, I'm asking a question. You cannot disagree. It's a question.
No, what did you learn? No. So here's the thing. So there's the whether or not computation would allow you to learn something about your theory you already didn't know. Yes, because a lot of things that might emerge from the simple theory that you start with are not, as you said, achievable by pen and paper, right? So what I gave you an example. What are the phases of a strongly interacting matter in the universe? Do we have a color superconducting phase? Do we have other exotic phases? I can't solve that. I know that it should arise from those two lines of equations of QCD, but I have no way to say whether there are these exotic phases. I don't have any experiment to explore it for me. I don't have access to the very core of neutron star, which is the densest part of the universe I can think of, to know what those phases are. So yes, I have to do the computation to learn something about what this theory would bring in those regimes of very exotic conditions, for example. So you still would learn from computations. The theory is not just two lines of action or Hamiltonian you write down. The theory is the emergent phenomena out of those interactions that are hard to compute, and then you learn something.
Right, you have learned something only in this case, in this example. I think you have learned only something after you've done the experiment, because as long as you didn't, you know what you're saying, I think, is it gives you an idea of where to go look for things. I guess that's what you're saying.
No, I thought the question was that have you learned something from computations or simulations? My argument is that yes. otherwise we wouldn't do this. Otherwise we wouldn't, why would I waste my time to just demonstrate that I can't simulate this theory? There has to be some questions unanswered so that I can use this tool. In the end of the day, simulation is just a tool to give me something about this theory that I didn't know about before.
Right. My question was not whether you learned something, it was whether we understood something. Not the same question.
Yeah, so it's very hard, right? When it comes to non-perturbative phenomena, it's very hard to understand where exactly this feature came from. One of the things that you can explore, because we can do simulation, is the dependence on various aspects of the theory. For example, if I change the masses of the quarks, was it that because the quarks had this particular mass that I ended up with this emergent phenomena? Was it that because this long-range part of nuclear interactions were more strong than the short range? If you start from that level of simulation, can I not change the relative scale of these interactions and then see the same thing? You can still investigate how is it that what was it the feature that actually contributed to the final answer, even though it went through this complicated non-perturbative procedure and you lost track of what was the cause of certain phenomena, right?
Okay, yeah, I agree. Yes.
Okay, so on that note of agreement, I think it's time to thank Zohreh again. This was really interesting, cool to see very different things towards what, like, I think most people in Cambridge at least work on when it comes to quantum computing, and also very exciting to see these amazing kind of experimental results that you guys are building at the University of Maryland.